Good morning to all of you. Let us now. What I want to tell you is that I have, created this file, which I'm just. I'm at page number 70. So I have. I'm using this file to so that you can take it as a kind of summary. I mean the complete file for random processes chapter. So the PPT is there, all the rules are there for proving a process to be cyclostationary or stationary, white sense stationary or white sense cyclostationary, and even ergodic. Those rules are there and with examples. So it will be easy for you to go through the file while you have to appear for the exam. The topic that I will cover today is I would like to cover 2-3 topics today, and I would rather try to finish the second chapter, because the third chapter, up to third chapter, is in your syllabus for the second quiz evaluation. All right, so that means I have, this is my first lecture of this week. That means I have around 6 lectures. To complete the syllabus for the second evaluation. All right. So I would like to finish this chapter, and if something will be left, I will cover that. But then I will, in the next lecture, I will start with the third chapter. But what I would like to cover today is, I would like to cover today is the cyclostationary random processes, because this is a very important topic. Cyclostationary random processes. You all know what is a random process. I have already explained. There are lectures present on your LMS also. Now, a random process xt, if I define a random process, if I denote a random process by xt, now, what is the meaning of cyclostationary? A random process xt is to be cyclostationary with period t. Cyclostationary means that it is stationary in a cycle kind. So within some period it will be stationary, then non-stationary, then again it will become stationary. I mean, within a period it will remain stationary. It's not purely stationary throughout. Within a period it will remain stationary. What is a stationary random process? Stationary random process is that in which the probability distribution function remains the same throughout the time period, throughout the time, right? You can refer to my previous notes for what is a stationary random process, what is a white sense stationary random process. To prove that a stationary process is a white sense stationary process, there are few rules, in which the first rule is that the mean of that mean of the random variable has to be constant. Then the autocorrelation function must depend on the time difference rather than the absolute times. So I would request you to please go through the notes, and you can refer to this file also. I have already uploaded this file, very I think nicely prepared file. You will feel that everything is available in that file regarding the second chapter. Okay, so let's come back to the topic. The topic is cyclostationary random processes. A random process xt is said to be cyclostationary with period capital T if the joint CDFs, if the joint cumulative distribution function of xt1, what is xt? Xt is a random process. Xt1 is a random variable, at time t1. xt2 is a random variable at time t2. xtk is the random variable at time tk. So the joint cumulative distribution function of these random variables and the joint distribution of if these if t1 is shifted by m integral multiple of capital T, and t2 is shifted by t plus mt, that means integral multiple of capital T. M is an integer here, and similarly for tk is shifted by mt, that means an integral multiple of capital T. T is the period. So the joint probability distribution function xt1 of xt1, xt2 and xt will be same as xt1 plus mt, xt2 plus mt, xtk plus mt are the same for all k, m and all choices of t1 to tk. So this process will be called as a cyclostationary process, right? The point that I want to mention here is that it is not stationary in full sense. It is not stationary throughout the time axis. But if this is a random variable, if xt is a random process, at time t1, this random process will become a random variable xt1, xt2 is another random variable, xtk is another random variable. The joint distribution of these random variables will be the same as xt1 plus m capital T, xt2 plus m capital T. So in between, the joint CDF will not be same. But at these particular sample points, T1 and T1 plus MT, T2 and T2 plus. So at these particular sample points, the joint cumulative distribution function of the two of this random process will be the same for all k, m and all choices of t1 and tk. So that's what is written here. The cumulative distribution function of these random variables xt1, t2, tk for values x1, x2 and up to xk is equal to the joint probability distribution function of xt1 plus mt subscript. This is in subscript. xt1, t2, xtk is in subscript. xt1 plus mt, xt2 plus mt, this is also in subscript of x1, x2 and xk. These values, if you put the values in the probability distribution function at this t1 or t1 plus mt, the cumulative distribution function will remain the same with a period capital T. So then this random process will be called as a cyclostationary random process, right? So another, special form of the cyclostationarity is the White-Sense stationary process. So xt is said to be White-Sense stationary if the mean of this random process with this time shift plus is equal to the mean of the random process at time t, and the auto covariance t1 plus mt, t2 plus mt is equal to auto covariance t1 comma t2. So these are the two conditions to prove that a random process is cyclostationary, but in the wide sense. This is not a strictly stationary. The first point refers to strictly stationary. This point refers to wide sense stationary, right? Let's take an example. This example is there in your tutorial sheet also. So I would like to finish or do some questions of tutorial sheet also today, right? Which is tutorial sheet number 8. Consider a random amplitude sinusoid. So in this is a random process given. Xt is a random process, and it is defined as a cos 2 pi t by capital T. So a is a random variable given, random amplitude. So a is a random variable given, right, with period capital T. So the period is capital T. Now we want to prove that is xt cyclostationary or wide sense, and we also want to know whether it is wide sense cyclostationary. Correct? So what is the cyclostationary concept? The cumulative distribution function is equal to of xt1 t2 is equal to f xt1 plus mt and so on. So let's check with that. This is my random process. So I can write this as probability of xt1 is less than equal to x1. What is the meaning of probability cyclostationary? Probability xt1 is less than equal to x1, x2 less than equal to x2, xtk is less than equal to xk, right? So I will put here the values. Xt is a cos 2 pi t capital T. So that means if I put it for xt1, it will be a cos 2 pi t1 by capital T is less than equal to x1 and so on up to tk. And if it is, and I can also say that a cos 2 pi t1 plus mt by capital T is less than equal to x1 if it is Whiteson stationary, right? So that means I'm taking the other value for t1 plus mt for tk plus mt. And if I use the property of the cos function, this will be x t1 plus mt is less than equal to x1 t2 plus mt. I mean, because over the full time period, the cos function will the output, the value of the cos function depending on the argument will remain the same, right? So t1 plus mt, if I do it like this, it's one and the same thing. Cos 2 pi t1 is actually equal to cos 2 pi t1 plus mt because it is over the whole period and so on. So I can write this as x t1 plus s. So I mean, what I want to say is that a cos 2 pi t1 by capital T is equal to a cos 2 pi t1 plus mt. So which is equal to x t1 is equal to x t1 plus mt. So I can write it. I can write the first equation. If you see, the first equation is actually equal to the fourth equation. So therefore, we can say that xt is a cyclostationary random process. All right. Then we can prove the it is Whiteson cyclostationary. We will have to take the mean and we will have to take the autocovariance, and we will be able to. We have already done this question, so that's why I'm not doing it here, right? So these are the two conditions which actually you need to prove to make it Whiteson cyclostationary. But what is the cyclostationary process? I have already explained. A random process xt is said to be cyclostationary with period capital T. If this condition is met, that means the probability distribution function is equal to this. These two equations have to be equal, right? And xt is said to be Whiteson cyclostationary if these are the conditions to be. If these conditions are true, then it is a Whiteson cyclostationary process. Okay. Then let's come to ergodic process. What is an ergodic process? To prove, to explain what is an ergodic process, I will actually stop sharing this screen. I will share another file which I have already uploaded. All right, which is at the name of ergodic process on your LMS. Okay, so this is the ergodic process and the conditions for ergodicity. Now, the first I have just explained the cyclostationary process. Now I will explain what is an ergodic random process. All these things are in your syllabus actually, and I will explain this with the help of an example. This example is a part of your tutorial sheet. Some questions, some 6th or 7th question in your tutorial sheet. Okay, let's look at the ergodic process. Now, a random process is said to be ergodic in mean. Actually, there are two conditions we need to understand while we say that a random process is an ergodic process, ergodic random process. The first condition is that a random process is said to be ergodic in mean if the ensemble average is equal to time average. Ensemble average is equal to time. And what is an ensemble average? Ensemble average is the usual expected value. If you look at here, ensemble average is actually the usual expected value. And this is given by, we know this formula, integral from minus infinity to plus infinity, x of this probability density function, x into probability density function, dx. Anji?
Your screen isn't shared.
Okay, just a minute. I'm sorry. Now it's okay? Hello?
Yes, sir.
Okay, okay. I'm sorry for that actually. All right. Now it's fine now because I have done the full screen.
Yes, sir.
Okay. So let me explain the ergodic random process. I have just explained you the cyclostationary process. Now it is ergodic random process. Now a random process is said to be ergodic. You must be, let me take 2-3 minutes on explaining why we are doing all these things. You must be wondering why we are doing these things. These things are very important because when you are conceptualizing a certain topic in your mind, right, as a process, it can be anything. What are the mathematical tools available to you which you will use to model that random process? And you will see that this subject is so important because it is mathematics, but you maybe, I don't know how much you will be able to appreciate this subject, but once you will go for the higher studies, you will definitely, and you try to look into some IEEE papers, which are based on certain maybe machine learning or artificial intelligence, signal processing, digital communication, even in any field, you will see that these topics are so important, actually the mathematical modeling, because you can write a program only when you have a certain mathematical model, right? Then only you can, or you will have to do on the basis of AI or machine learning, but still you need to know the fundamentals of mathematics, with which you can actually model a random process. Or a random, I mean, not a random process, I mean any real-time problem. All right, so let's start going to those issues. Sometimes if the things will allow, I will explain you the applications and the advantages of studying this subject, and what is the importance of what is the correlation of studying this subject into your future coming subjects. Anyway, I hope you will appreciate at least that this subject is important. Because this is mathematics, it may be a little dry subject, but this is very important. You must know the fundamentals of this course. So a random process is said to be ergodic in mean. So there are two conditions to be understood while saying that a random process is an ergodic process. First is that it has to be ergodic in mean, and it has to be ergodic in autocorrelation. What is the meaning of ergodic in mean? What is the meaning? There are two averages I am talking about here. One is the ensemble average. Ensemble average is just the mean that we used to calculate in our previous topics. It is the expected value of this random process xt, or a random variable, and this is given by minus infinity to infinity x of probability density function dx. This is normal expected value. All right. Now, what is time average? Time average means what we will do, we will take limits from minus t to capital T, and we will try to ensemble average is actually the expected value, I mean, which you are expecting as a mean. Time average is the actual value when you have done the measurements from minus t to capital T, and this is the formula. Limit t, capital T approaches infinity, 1 by t of xt dt, and we are looking for the average within this time period only, minus t to t. This is known as time average. Now, a random process is said to be ergodic in mean if the ensemble average is equal to time average. If you remember, I did the law of large numbers, in which we said that when n approaches infinity, the mean is the relative mean is equal to the ensemble mean, or the actual mean, expected value. So that means total law of large numbers is basically explaining an ergodic process. So a random process is said to be an ergodic in mean if the ensemble average is equal to the time average. That's the first condition for a random process to be ergodic. And what is the second condition? A random process is said to be ergodic in autocorrelation if time average autocorrelation function is equal to ensemble average autocorrelation function. Now, what is the ensemble average autocorrelation function? We know that, we have studied it. Rx tau is equal to xt, expected value of what? Xt into xt plus tau. This is the ensemble expected value of the autocorrelation function. It is given by xt into xt plus tau, ensemble average autocorrelation function. Now, what is time average autocorrelation function? This is the integration limit t approaches infinity 1 by 2t and limits of integral are minus t to capital T xt t plus xt into xt plus tau d tau. So this is time average. These are the actual measurements. This is the expected or the ensemble autocorrelation function. If these two conditions are satisfied, we can say that this random process is an ergodic random process. So let us take an example, and this example I have put in the cheat sheet number 8 also. I think probably it's the 7th question. You will see. So the question says that consider a random process xt. This random process is given xt equal to a cos 2 pi fct plus phi. Phi is some phase, fc is some frequency, and a is the amplitude. Now, what are the conditions for this random process? A and fc are constants. So for this random process, a and fc are constants. Had phi also been constant, then it would have been a deterministic process. But this is a random process because phi is a random variable, right? So it's a random process. Xt is a random process. A cos 2 pi fct plus phi. Phi fc and a are constants. Phi is a random variable. But what is the distribution of this random variable? Uniformly distributed in the interval 0, 2 pi. So this random variable phi is uniformly distributed from 0 to 2 pi. Now we need to check whether this xt is ergodic. So we know what is an ergodic process. It has to meet these two conditions. It has to be ergodic in mean. It has to be ergodic in autocorrelation function. So let's prove that. We need to check time average is equal to ensemble average. Time average autocorrelation function is equal to average ensemble average autocorrelation function. Since phi is only the random variable, others are constants. So we are given what we are given. I'm using let this phi be theta, right? So I'm using here phi, but rest of the question I solved with theta. Anyway, this phi is actually theta. So please make the correction. All right. Now, let me just explain. So we need to check whether the time average is equal to ensemble average and the time average autocorrelation function is equal to the ensemble average autocorrelation function. So theta is the random variable. So that means from 0 to 2 pi, this random variable is given to be uniformly distributed. From 0 to 2 pi, this is uniformly distributed. So if we try to find out the probability density function of this f subscript theta of theta, that means this is the PDF of phase of this signal. This is 1 by 2 pi. Why it is 1 by 2 pi? Because we know that if it is uniformly distributed, the area under the curve has to be 1. Now from 0 to 2 pi, this is the length of this rectangle. 2 pi is the length of the rectangle and the width has to be 1 to pi so that the area under the curve is because along y-axis is the PDF, it has to be 1 over 2 pi because the length is 2 pi. So 1 over 2 pi multiplied by 2 pi has to be 1, the area under the curve. So that's why we will say that f subscript theta of theta is 1 by 2 pi. Within this range, 0 to theta, 0 is less than equal to theta is less than equal to 2 pi. This is given, this is uniformly distributed and 0 elsewhere. So we want to find out the mean because we need to find out the ensembled mean first of all. What is the ensembled mean? It is given by xt of probability density function dx. What is xt? Xt is this a cos 2 pi fct plus phi, or I'm sorry, this is theta. A cos 2 pi fc plus theta. And what is the density function? It is f theta theta. And this f subscript theta of theta is 1 over 2 pi. So I will write x of t into the probability density function. and with respect to theta, this is the integral, and the integral, the period will be from 0 to 2 pi, because otherwise it is 0. So if you solve this integral, this integral will be 0, because cos of 2 pi fct plus theta, and this is the limits of the integral are from 0 to 2 pi. That means over the full period, the average value of the cos function will be 0. That we know, right? So we will say that the ensemble average is 0 of this random process. So it is 0. Now let us look at the time average now, because we have to prove basically the okay, I don't know whether for time average, the formula is xt, this is the integral, limit t approaches infinity, minus t of t, xt t plus tau, right? So if you will solve this, actually time average will also be equal to 0. You will find that. Let me just, time average is what is time average? Let me try to solve it. Limit t approaches infinity, 1 over 2t minus 2t to t of xt dt. So what is time average will also be 0, because it is from 0 to 2 pi, and the time average formula I have said it to be limit t approaches infinity, 1 over 2t, and this limits will be 0 to 2 pi xt. Xt is our a cos 2 pi fct plus theta, and since we are integrating a cos function over 0 to 2 pi, and then we are taking the limit, this will again be 0, right? So it is so time average is equal to the ensemble average. So that means we have proved the first condition, that a random process is ergodic. This random process is ergodic in mean. Now we have to look for the second condition, which is a random process, which is the autocorrelation function. What is the autocorrelation function? The autocorrelation function is given by Rx of, this is the ensemble autocorrelation function. Xt1, expected value of xt1, t2. What is xt1? 2 pi cos f, 2 a cos 2 pi fc t1 plus theta. And what is xt2? Is a cos 2 pi fc t2 plus theta. Now, if you use this formula, cos A cos B is half of cos A plus B plus cos A minus B, you will be able to reach to this equation, right? And if you solve it further, I have already solved this integral. If you will solve this, then you will find that this will come out to be a square by 2 cos 2 pi fc t minus 2. What is this? This is the ensemble average, ensemble autocorrelation, ensemble average autocorrelation function. Then we have to find the time average autocorrelation function. Let's go to the next page. The time average autocorrelation function. Mean is constant. We have already proved. The the ensemble average autocorrelation function is a square by 2. This is if you see, we have already proved a square by 2 cos of 2 pi fc t1 minus 2 t2. We can replace it with tau. That's the time difference, right? So this is a square by 2 cos of 2 pi fc tau. Now we have to find out the I have proved it here that time average mean is actually 0. As I told you that you are integrating from 0 to 2 pi, and this cos function will be 0, and expectation. So that means we have already proved that expectation is equal to time average. That means the first condition is met. And we have already seen what is the ensemble average autocorrelation function. This is given by a square by 2 cos 2 pi fc tau. Now we have to calculate the time average autocorrelation. Time average autocorrelation function is given by limit t approaches infinity of 1 over 2t minus t to capital T xt into xt plus tau. So I have given you the solution using the same trigonometric formula. You will be able to prove that the time average autocorrelation function also comes out to be a square by 2 cos 2 pi fc tau. So this proves that for this random process, which is given xt equal to a cos 2 pi fc t plus theta, I am solving it with theta. This random process is ergodic in mean. That means the time average is equal to the ensemble average, and it is and the time average autocorrelation function is equal to the ensemble average autocorrelation. I am giving you the formulas also of the time average mean and the ensemble average mean, time average autocorrelation function and the ensemble average autocorrelation function. Use these formulas to prove these two conditions, and in the tutorial sheet also I have given this example, and for this example you will prove these two conditions to say that this process is a random is an ergodic process. It is ergodic in mean, time average is equal to ensemble average, it is ergodic in autocorrelation function, time average autocorrelation function is equal to the ensemble average autocorrelation function. That's an ergodic process, right? Okay, so what we have done today, we have done with cyclostationarity. Very simple. I am giving you with example. I'm trying to explain you with examples, which I have included in the tutorial sheets also. Only thing you need to learn is what is a random process, what is a stationary process, what is a non-stationary process, what is a wide sense stationary process, what is cyclostationarity, what is wide sense stationarity and cyclostationarity, what is an ergodic process, right? These things you have to, and there are certain conditions. You must know what are the conditions, and at least you will make your mind, you will have in your mind what are these processes. Now the question comes whether a particular random process is given in the form of a mathematical equation, and you will be able to prove that, you will be able to solve that or not. But at least theoretically, you must know that these processes are there. Hold on, let me tell you an example before I come to the moving average and other things. For example, all the speech compression algorithms. Speech compression algorithm, all the audio compression that you do in your mobile phone, or even the video compressions that you do in your mobile phone, are related with they take the fundamentals of mathematics from these topics. Okay, so now let us look at 2-3 more important concepts for which I will stop sharing this screen, and I will use the another file which I have uploaded. Yeah. Okay, I'm sorry. This is the file. All right. All right. I will share the screen. And let me do the full screen mode. Is it the next PPT is visible? Hello?
Yes,
Yeah.
sir, it is visible.
Okay. Some very basic concepts, very basic concepts I will discuss, which you will find in your DSP systems, digital communication systems, stock markets, the biological behavior of molecules, the number of things. So what are the important terms, right? Now the first important, this is also uploaded on your LMS. Every notes is on your LMS already. Now, what there are few important terminologies associated with random process. One is we call a random process to be a moving average random process. Then we call a random process to be autoregressive random process, and we also call a random process to be autoregressive moving average. Right? So let us try to understand first of all, what is a moving average process. Now, this is I will give you the crux of the process. Let's not go into the details of all these things, but the crux of the topic is here. Let us say xt is a random process, and of course I will call this this process as a moving average process. Now xt, of course, this is time, t is time, and this is equal to some error term, right? And some error term plus this. If I say moving average process of order 1, so that means I am including this error term at time t, and I am including the error term at t minus 1. So therefore, it is moving average process of order 1. If I will include epsilon t minus 2, then it will be moving average process of order 2, and so on. So epsilon is some kind of constant or error disturbance term in this moving average process of order 1, and plus theta is some constant et minus 1. So this is the system equation for a moving average process of order 1. Order 1 because only one lag term is there. So this is lagging. This term is actually the lag term, lag term in terms of error. This is lag error term. So error term plus some constant into the lagged error term. So this is how we will define this moving average random process. As an example, we can say that we want to see the change in demand for orange juice at time t, and this is equal to epsilon t minus 0.5. 0.5 is the constant that I'm choosing, epsilon t minus 1. So this is change in demand for orange juice at time t, maybe daily data we are taking. So this is the some kind of disturbance. What this disturbance can be, as an example I'm taking. We want to know the change in demand for the orange juice, right, at time t. And at time t, certain disturbance has come, maybe a certain change in the temperature, right? Temperature Et is greater than 0. If Et is greater than 0, because initially, if I will assume this epsilon t minus 1 is 0, so that means the change in demand is actually dependent on the change in temperature, which is this epsilon term. So because epsilon t is greater than 0, so definitely there will be increase in demand. And I'm assuming t minus 1 is 0. Right. So Et represents what? Et represents the change in temperature, disturbance, which is actually telling me, this equation is telling me when there is a change in the temperature, there will be increase in the demand of orange juice. So intuitively, it seems to be correct. And I'm assuming that epsilon t minus 1 is 0. So this term goes to 0. But next time, let's say there is no change in the temperature. That means Et is 0. That means because next time will be epsilon t plus 1. Next, if I'm talking about the demand for orange juice in the next interval, it will be t plus 1, and this will again be t plus 1. And if there is no change in the temperature, so that means epsilon t plus 1 is 0. If epsilon t plus 1 is 0, the change in demand for the orange juice is actually equal to minus 0.5 epsilon t. There will be decrease in orange juice demand. When the temperature has not changed, there will be decrease in the this part of the equation is telling me there will be decrease in the orange juice temperature. All right. So that seems to be quite self-intuitive. This is just an example, and this is how we represent the moving average process of order 1. If it is order 2, I have already explained, there will be more terms. Now, what is auto-regressive? Please remember this equation. There is no x term here. xt is the random process at t. This is equal to error term plus theta et minus 1. Let's look at auto-regressive. What is auto-regressive? The equation to represent an auto-regressive process of order 1 is xt equal to rho xt minus 1 plus et. Et is, of course, and let me explain it here. Et is a IID process, identically distributed independent process with 0 mean and sigma square. These are the statistical parameters we are assuming for the error term, for the moving average. And for the for explaining the auto-regressive process, we are also assuming, the ET is an identically independent and identically distributed with 0 mean, sigma square as the variance. But this process is given by xt plus rho. Rho is some constant. Xt minus 1. Xt is the corresponding to the previous term plus the error term. Why it is called auto-regress? Why the word regressive is there? What is the meaning of regressive? Regress means to go back to a previous condition. Regress means xt is the present time random process, and xt minus 1 is the previous time random process. Regress means to go back to a previous condition. So we are going in the auto-regressive process, we are going back to the previous condition. That means this random process at time t1, time t is equal to rho is some constant, xt minus 1 plus epsilon t. This is how we will represent the auto-regressive process of order 1. Order 2 will be, if we will include xt minus 2 also. Order 3 will be xt minus 3, and so on. So xt equal to rho 1 xt minus 1, rho 2 xt minus 2 plus epsilon t. This is auto-regressive process for for order 2. It can be related with with the oil prices change, right? Where oil prices change in the oil prices will depend on at time t, will depend on the change in the oil prices at time t1 also with some error term. The error term can, disturbance term can be some explosion in the oil refinery, so it may change the demand in the oil prices, right? So, but this is the important condition, that an auto-regressive process can be explained with this equation. Now, auto-regressive 1 is stationary and non-stationary. So let's look at AR1 to be stationary and non. For a stationary process, this is the auto-regressive stationary process. Xt is equal to rho xt minus 1 plus epsilon t. Non-stationary. What is non-stationary? Here rho will be equal to 1. Xt equal to xt minus 1 plus epsilon t. So this is a non-stationary process. What is the meaning? Let's say this is the random process. It looks like noise, but this is, let's say, some random process. You will see in this random process the value of this random probability distribution density function will come to 0, will return. This stationary process has a tendency to bring the PDF back to 0. If this is for, let's say, 0.7, and there will not be any positive and negative the crests and troughs, positive troughs and negative troughs in the stationary process when rho equal to 0.7. But when rho equal to 0.95, you will see that there will be some positive and negative indications, but again they will try to come back to 0 in a stationary process, and that will be controlled by rho. Rho is a force actually. When it tends towards positive, rho tries to bring it to 0. When it tends to become to negative, rho tries to bring it to 0. So rho is a parameter which will try to bring the random this random autoregressive random process, which is stationary, to move like returns to 0 quickly. With rho 0.7 returns to 0 quickly, 0.95 will return to 0, but maybe little. But with a non-stationary process, it will take, if it is in the negative direction, it will continue for large number of large amount of time. It will be negative. It will be positive. It will be for large amount of time. It will be positive. And if it is negative, very long, it will come to 0. It theoretically it will come to 0, but it will come after a long time, because there is no rho in the non-stationary process. Rho is 1 here. There is no force which is bringing the probability distribution function to go back to 0. That's the difference between autoregressive process, which is stationary, and non-stationary. Now, what is the reason for this? The reason to, yeah, in both cases, unconditional means are 0, but for conditional means, conditional means in the first case, in the stationary case, is equal to rho of xt minus 1, and the conditional mean in the case of second, which is non-stationary, is equal to xt minus 1. Rho puts pressure for graph to return. So as I was just trying to explain, rho is not there, so no pressure. That's a parameter that cannot force the random process, the probability distribution of the random process to go back to 0. Now there is another process which is known as ARMA, which is autoregressive moving average 1, 1. Autoregressive of order 1, moving average of order 1. So let's look at here. Xt equal to rho of, this is xt minus 1. I'm sorry for here. This is rho xt minus 1 plus, this is for the autoregressive part, epsilon t minus theta epsilon t minus 1. This is for the moving average part, right? So this is the equation for the ARMA process. And this is a question in your tube sheet, that a random walk is a autoregressive process of order 1, and it's a non-stationary time series. So if it is an autoregressive, a random walk is an autoregressive process of order 1. This is given. I can write it to be xt equal to xt minus 1 plus epsilon t. Epsilon t is IID with mean 0 and sigma square as the variance. So if I just try to continue iteratively, recursively go back, it is xt minus 2 plus epsilon t minus 1 plus epsilon t. And I can put it in a general form, put it here 0 and sigma I going from 0 to t minus 1 epsilon t minus 1. This is the recursion I'm using here. Now, properties of the air process with rho equal to 1, that the expected value is expected value at t, expected value is equal to the expected value of the right hand side, and this is the equation, right? So this is going to be 0 because the IID, this mean is this is an epsilon t is an IID with mean 0. So this is going to be 0. This expected value of the random process is x, which is again 0, and so therefore ext, expected value of xt is equal to ex0, the right hand side, which means that the mean is constant. Mean is constant means it's the first condition for proving it to be stationary or non-stationary. But if you calculate the variance, variance of xt is equal to 0 to t minus 1 variance of epsilon t minus 1. Right. So variance is given here sigma square of 1 epsilon value, but it is from 0 to t minus 1. That means t values are there, t of sigma square. So that means the variance is a function of time. Once the variance is a function of time, it is not constant. If the variance is not constant, the second condition for stationary and non-stationary is not met. So therefore, if it is a function of time, I can say that the random process is non-stationary time series, because it becomes a function of time. So just 2-3 definitions were there: moving average, the autoregressive, and the autoregressive moving average process, right? So in this chapter, we have covered the random processes. In the random process, we try to study what is a stationary and non-stationary random process. What is a stationary random process? What is, what is a strictly stationary random process? What is a wide sense stationary random process? All right. Then what is a non-stationary process? How to prove that? Then we have tried to study what is random walk. Then what is today we have studied what is a cyclostationary process, what is ergodic process, and then we have tried to study what are moving average, autoregressive, and autoregressive moving average concepts. So please go through the slides that I have uploaded on LMS, and you can come back to me with any questions you have. I will end this lecture here. Thank you very much.